Hello everyone, and welcome to today's webinar, Generative Design and Additive Manufacturing, a powerful combination. Today I'm very happy that we can enlighten you a little bit more about additive manufacturing and generative design. And especially we will enlighten you on how the combination of those two technologies can push your designs. I wouldn't be doing that alone. I have invited Scott Green, Principal Solution Leader at 3D Systems. He's with us. Good morning, Scott.
Hi, good morning. Thanks for joining us.
Well, I would like to thank you as well, Scott, for joining us and bringing your knowledge into this webinar. Let's start with a quick introduction of you and me, so that all attendees know what our field of application is, and let's kick off the webinar after that.
Yeah, hey, again, thanks everyone for joining us. I'm Scott Green and a Principal Solution Leader at 3D Systems for the Semiconductor segment. So not only am I a semiconductor subject matter expert, but I've also got a long history at 3D Systems in the software business unit, in product management, and in various sales management functions. My background is in electrical engineering from University of Maryland, and I've spent time at Stanford University studying bioengineering and bioinnovation.
Okay, thank you very much, Scott. Maybe for the listeners who don't know me yet, I'm Gert-Jan. I'm one of the AI design engineers at Diabatix, and I do have a master's degree in mechanical engineering at the University of Leuven, and my background is especially in automotive engineering. And within Diabatix, I'm guiding thermal engineers and thermal architects through the process of adopting generative design in their workflow. So that was a little bit of an introduction about us. We will quickly introduce the two participating companies, 3D Systems and Diabatix as well, with a little deep dive in our technologies, because we quickly want to give an introduction on that before showing how to combine them. And we will talk a bit more then about a common case study that we did, so with 3D Systems and Diabatix. And that's a case study for the semiconductor industry. So we will talk very briefly about the challenges that there are over there, especially in the thermal management. And we will compare then the traditional design strategies with the design strategy that Scott and I took, or that both our teams took, in order to solve this problem and to get to better solutions. In the end, we quickly summarize what the elements of these solutions were, and of course we have a little dive in how you could learn more, or how you could get more information. But let's start with a quick introduction of the two technologies.
Yeah, first I'll start off by talking a bit about 3D Systems. 3D Systems is organized into two major solution groups. On one side, you've got the healthcare solution group with some segments inside. On the other side, you've got the industrial solution group with segments inside. And I manage the semiconductor solutions segment. And as you can see, we are hyper-focused on providing full solutions to industrial segments, as you see on the screen, including energy, aerospace, consumer, transportation, motorsports, as well as green technology. Next slide, please. In 3D Systems, a little bit of background on us. We developed the first SLA 3D printers, so you could say we invented 3D printing about 40 years ago. And not only are we the company that invented 3D printing, but we've continued to innovate over our nearly 40-year history. So as you can see, we have a continuous innovation, and here's just a sample of some of our latest. Next slide, please. And we use a very unique approach to helping our customers be successful with additive manufacturing. And it's going to be about a 5 to 6 stage approach, which allows us to start with a feasibility study and an exploration and applications or potential problem solving exercise. And following that, after we find some low-hanging fruit together, what we want to do is try to innovate. And once you've decided, or a customer has decided to make a transition to additive, we try to figure out how to make the best use of additive technology, and that includes working with our friends such as Diabatix to really cram as much value as possible into the transition to additive manufacturing of legacy parts or brand new designs. And then we continue on to develop the actual manufacturing process and validate its compliance with your requirements, and then figure out how to either produce in a short run or batch production, or transition that production off to a manufacturer which can really scale up. So our business is not a service bureau, but what we do is solve problems and do bridge production or long-term production for our customers. But ideally, we want to help take that whole package of information and transfer that technology off to a supplier, which can help scale it to large quantities. Next slide, please. Thank you. And then again, we do have over 150 machines working 24 hours a day, 365 days a year in highly regulated industries. So we have all the appropriate certifications to do highly regulated work. And I like to say we specialize in torque as opposed to speed, because what we can do is offer batch production solutions across the whole range of materials that we do have. And 3D Systems performs this process out of many facilities that we have across the United States and globally. So you can see our innovation centers are based in Littleton, Colorado. We have one in South Carolina. We have them in California, Leuven, Belgium, and also a location in Germany. And we're running over 150 metal machines nonstop, 24 hours a day and 7 days a week in highly regulated industries. As you can see, we have all the ISO and ISO certifications to operate in FDA environments as well as aerospace. And I like to say we specialize in torque, which means what we can do is offer the broadest range of capabilities across all of our materials and across all post-processing capabilities to really certify and create a process that can be scaled up. Next slide, please.
Okay, thank you very much, Scott. Let's take a quick deep dive as well into the technology of Diabatix. Diabatix, the company itself, was founded in 2016 in Belgium, and we specialize in generative thermal design. And by doing that, we try to innovate the way thermal engineering is done, and we try to basically guide thermal engineers, thermal architects to a new workflow. And this new workflow, if we evaluate it over our clients, typically what we see is end ups in 30% better thermal performances. I think the use case of today is an excellent example of that. And the technology that we use easily generates over 500 designs or 500 iterations over every or to get to a solution with computing system, so it can do it super fast to come to, in the end, the best solution. So in total, over the years, we used several 10 of millions hours of CPUs, and the designs that we generated over that period is, of course, huge. The way we do that is we apply generative design, and basically we wanted to get rid of the conventional way of engineering, where engineers approach designs with making CAD models, simulate it, go back to the drawing table, reshape the CAD model, simulate it again, and we try to fully automate the design cycle to get to optimal heat sinks in no engineering time. So that's beside the thermal performance gain, we try to focus as well on reducing engineering time. We know all your time is limited, and if we can automate a part of the design job, I think that's a useful case for everybody, especially in complex situations like the semicon example that we have today. And this technology nowadays is applicable in a lot of industries. If I have a look for the most common industries that we see nowadays, where generative design for thermal applications is applied, I'm looking into data center cooling, aerospace, electronics, laser cooling, where you have a very high dense or high power density, automotive, of course, because there the challenge is very big with the switch to electrical mobility, and as we will see further on in the webinar, of course, the semiconductor industry, where especially temperature variance is really important. To get you familiar with the technology, I'm showing you one short movie on how a design is generated, just to give you a look on how generative design works. What you can see happening in here is one design run where 500 to 1,000 iterations are happening. And in each of these iterations, a design is created and is analyzed. And based on this analysis, a new design is created and is improved. And by letting the computer just do over and over again, you get to better results. So that's, let's say, generative design in a glance. The biggest benefit of that is that you can create very complex boundary situations, very complex constraints, and so on. It's a computer system, so it can handle that as long as you put enough computational power in the back. And by handling these complex situations, you can come to very good results, which are, as engineers, very hard to achieve because of complex situations.
And with that, I'd like to take a look at some of the issues related to semiconductor capital equipment manufacturing, as well as semiconductor supply chain. So we'll give a little bit of insight on what's happening with the chip shortage and what's going on in the semiconductor capital equipment industry. Now, if you're not familiar with semiconductor capital equipment, it's really cutting edge, highly precise and very sensitive equipment. And really, as you can see here, and this is just a portion of a piece of capital equipment, a lithography machine. You can see it's quite complex. There's hundreds of thousands of components and kilometers of wire and tubing that go into them, and temperatures must be very stable. Particle counts and particle counts for contamination must be very, very low. So there's very strict cleanliness and precision requirements, and it's very critical. This equipment is very critical to feeding the silicon wafer product into the supply chain so that we can all buy our phones and drive our cars, and we're all feeling that pain right now. So, right now supply chains have been disrupted, and that doesn't mean just getting the product into your computers or your electronic devices. So as you can see, you've got a very complex manufacturing system or manufacturing tool. There's a supply chain that feeds that too. So in order for foundries which make use of this equipment to produce silicon wafer product, they also need to produce capital equipment, which is highly complex. So because of the pandemic, supply chains have been put into disarray, and that's caused countries and private businesses to react and make sure that they reallocate the balance of equipment and capability across countries. So you can't just put everything in China anymore because that's too fragile. Equipment and foundries are being set up all over the place to be a much more even distribution and a more resilient supply chain to feed semiconductor product. And that means that more capital equipment is being made faster to set those foundries up. And because of that, there's an opportunity that the industry is taking to innovate and engineer this solutions for the current generation of systems, but also that next generation of system, which will be more resilient. Now let's talk a little bit more about some applications. Next slide, please. Thank you. Now here's just a cross-section view of one such example of a piece of capital equipment. Now there's dozens of different types of very specialized equipment that go into making silicon wafer product, and this is just an example of a lithography machine. And here you can see some bubbles which talk about the different types of places where high precision components and high-tech engineering is put into manufacturing of this equipment. And we're going to talk more specifically about three of these. Next slide, please. And there are three such examples that are really clear examples of where additive manufacturing and high quality design or generative design can contribute to this space. And those are wafer table thermal management, which will be the subject of the rest of this presentation, And also there's opportunity for flexure, optical flexure integration, as well as structural optimization of components which need to have high strength to weight ratio. And of course, in wetter processes or hydraulic applications, optimizing manifolds for smooth or laminar fluid flow and reduced disturbance in a line is quite critical. But today we're going to take most of our look today is going to be at the wafer table thermal management. So let's talk about some of the challenges related to that. Now, in a typical kind of problem description, we want to talk about the challenges associated with it and the benefits of the solution. And some of the challenges that you have with wafer table thermal management is you typically have cross-functional design committees. So many people involved in trying to develop this machine and every single component involved in it. So that actually, the more people you have involved, the slower sometimes a process happens. And specific technical problems you have are you want to maintain the most even temperature across the surface of that wafer as possible. And there are several reasons for that. Sometimes you need to condition or relieve stress on a wafer so it stays very flat during a process. And then later you may want to keep that temperature at a stable state during the lithography or deposition or photoresist strip process. So because of that, it's very important to have the ability to precisely control temperature gradients as well as time to cooling. And then additionally, for any complex component, you always have some sort of assembly, quality, serviceability, or component longevity issues. Anywhere there's a weld or an assembly, you have a point of failure. So it's preferred to have single monolithic, functionally consolidated parts over assembled parts, not only because of serviceability, but also production time. It's much faster to make those. And then again, because of the semiconductor supply shortage, production and productivity is always going to be a concern where we're trying to crank out more wafers as fast as possible with better quality. So anything that is going to reduce or shave off seconds in cycle time is going to be helpful. And now the benefits of generative design and additive manufacturing together mean that you can generate precise geometries that satisfy specific requirements automatically. And with additive manufacturing, you can really rapidly iterate on those complex geometries inside of one design architecture, such as a wafer table. And with the generative design, you can actually, again, precisely meet those temperature requirements, turbulence, pressure, vibration requirements, and benefit from the design consolidation that's possible, design freedom of additive manufacturing. Let's take a closer look at some of our generations of wafer tables. You may be familiar with this wafer table. This is our first generation wafer table, just to give you a look at what's inside in this cross-section view. So with precision calculation and better design architecture for wafer table thermal management, you can reach new levels of performance and productivity and quality through the process. And this was our first generation of our wafer table demonstrator. And our next slide, please. And we took this concept and built on it, and this is the second generation of our wafer table demonstrator, which includes not only a cooling pattern, but also integrated air blade for a gas flow barrier, a generatively optimized support pedestal, as well as vibration dampeners and integrated cooling lines. So you can actually take this concept of just cooling a surface and combine it with all other types of geometry and functional consolidation that you may need. So we representing here another step change in our understanding and our demonstration of design consolidation for thermal management. And the next thing we're going to discuss is a deep dive on this cooling structure. So let's talk really deeply about cooling structures and how they can benefit silicon wafer manufacturing. You may have seen our Metal AM article, which is a case study on optimal cooling structure design. And here's a quick look at the end result that we're going to go over in our next slides. Now, traditionally, let's talk about traditional design first. Traditionally, in order to create a cooling pattern, we start with a best guess in traditional design in parametric CAD to hit some specific requirements. And the requirements of a wafer table are going to be low pressure loss. So you want to make sure that you're not overcompensating or pushing too much fluid into the system and then losing that pressure with a super long line or inefficient cooling pattern. You also have a requirement for very low temperature gradient across the surface. And that's a measurement of how much you're allowed to fluctuate in your temperature across that surface. And that requirement means that you must have very good heat spread or cooling spread. So you need to be able to control that temperature within a very narrow band across that surface. And anywhere possible, you need to be able to have a short cooling time or short heat up time, as well as a rapid thermal response. So if things change and you need to compensate and overcool or overheat to compensate for an environmental situation, that thermal response needs to be very precise again, and this affects productivity. Also, you need to consider the fact that when you're creating a very complex component that may be traditionally manufactured out of multiple pieces through machining and braze welding, you need to consider the fact that the part needs to be long-term stable with no leaks, and it also needs to be mechanically stable, so you need to reduce any chance of vibration or variability in that process, because in semiconductor capital equipment, productivity and success relies on the system working as close to theoretical values as possible. So you need to create that environment inside the machine. And finally, from a manufacturing perspective, with traditional design, you're going to have so many limitations with what you can do that typically you've got a lot of design for manufacturing constraints. And when trying to transition this to additive manufacturing, all of these things need to be considered simultaneously, and that actually involves quite a lot of people and iteration with tools on the market today. And now the Diabatix solution offers you efficiencies that we're going to talk about in the following slides. Let's talk a little bit more about the limitations of traditional parametric design. Now, best guess is typically the way most thermal engineers start, using some design simulation or thermal simulation. They make some best guess at how the pattern the patterns that they can implement based on things that they know from the past. Now, the problem with that is if you're using a parametric framework for a design architecture and trying to edit that in the traditional BREP CAD environment, there's many limitations there. A parametric design setup will allow you to have some iterations and customization of a design strategy, but it's easily breakable. It's not necessarily going to work for every single design iteration. So there's a very narrow window of parameters that you can change in order to get a quality result. And as you can see on the right, here's a design architecture that has some parameter adjustments associated with it, and you can see it being easily broken when parameters pass a threshold value. So that traditional best guess approach is not ideal for precision cooling requirements or high productivity cooling requirements. It also doesn't take advantage of the value of additive manufacturing. To some degree, it may, but this design here is easily machinable. But then again, if you go to machining, you have to deal with traditional assembly and welding for consolidation of the design. And this does require a lot of lead time for traditional manufacturing, testing, simulation, and a lot of people involved in order to validate that design. And again, you're constrained to a single design architecture, so you cannot take this design architecture and decide you're going to add serpentine channels to it. It requires even more work.
Okay, thank you, Scott, for explaining a little bit about parametric design already. Now, one of the things that we did together in this case study was making a few traditional designs or parametrically optimized designs, just to see how they would behave if you would compare it with a design which was created with a combination of generative design and additive manufacturing. And one of the first designs that we ended up with was a pin fin design, as you can see on the right bottom of the slide here, which is very easy to deploy. It's very easy to create. Also, if you want to or want to optimize this in a parametric way, it's easy to define your parameters like pin distance, pin fin diameter, and so on. But the disadvantage of that is it's not very of a complex design, and I'm not saying that complex designs are required, but the disadvantage here is the flow always follows the path of the lowest resistance. That's just the basic physics, and if you evaluate this design, then the fluid is going straight from the inlet to the outlet, and that is just creating some hotspots. Basically, your fluid is not spreading enough. Besides that, the gap between the pins needs to be very small, which again adds some challenges from other perspectives. And if we evaluate then how this behaves, and I summarized 3 key parameters there. First of all, you see the thermal gradient, which was at 0.12 degrees Celsius for this design, which was way too high. A pressure drop of 22 kilopascal, which was very good. Because the limit was at 70 kilopascal, but yeah, still it's not solving the issue of a minimal thermal gradient that you want to have in these cases. And the time to a stable temperature was at 410 seconds. Now, that's not the only design that we created. One of the other typical designs that you see coming with this time or this way of designing is serpentine channels. So we designed one as well. We optimized it with parametric optimization, and you see that from thermal gradient point of view, this design is behaving very well at 0.09 degrees Celsius, but the pressure drop was way too high. We ended up with 420 kilopascal. Again, the limit was at 70 kilopascal, meaning your system cannot handle this. So it's useless in the end. Although time to stable 409 seconds, which is a little bit better than the previous design, but it's useless. The pressure drop is way too high. That's only from or evaluated from a thermal perspective. If we evaluate it as well from a manufacturing point of view, it is possible, but it's a very hard job to do the power removal and chemical cleaning afterwards to get to finished part in a decent way. That comes due to the long lines, the sharp turns, and so on. That is not only causing pressure drop, but it's also causing some difficulties in manufacturing. So those are 2 typical designs that you would see with the conventional way of engineering. If I may speak in my experience of thermal engineering, those are the types of designs that you see coming everywhere in every application, from aerospace to automotive to electronics. Pin fins design, serpentine design are always the designs that come back. Why? Because as engineers, we are limited in how far we can think. We have a limited imagination, and this is something which we have learned, which we have seen at other projects and so on. And from a very natural human way, we always are getting back to those designs. And the limitation there is you pick 1 or 2, like we did in this case. You optimize that, and I'm quite sure with parametric optimization that you can get to the best design possible for that concept. But the problem is that you selected a concept already. In the previous slide, you selected a pin fin design. In this slide, you selected a serpentine design, and you can optimize those, but it might still be that there was another concept that you would have not thought on, which would end up in a better design. And that's a little bit of the problem with or that's why Diabatix is trying to change the way thermal engineering is approached. We want to get rid of selecting that concept. First of all, it costs a lot of time to do that, and you will get to a solution with that way of working, but it will never be the best way of working. And the approach that we developed is actually bringing in generative design there. And describing the problem will be more or less the same. So you start from a certain geometry, you sit together with your colleagues and you decide or define what the design envelope is, you decide what the boundary conditions are and what your design targets are. So that first step is a little bit of the same. And then instead of that you are going to go to your CAD environment and start designing that, you just enter that into a generative design platform. For us, that's Diabatix Gulsion, which I will also demonstrate in a minute. And what you do there is basically explain the software, the same things as what you would explain to a colleague of you if you would ask him to create that design for you. So you would tell him, again, those are the boundary conditions, this is the design envelope that you have, these are all the parameters, and this is what we try to design for. And once you have done that, and that's a matter of 15 minutes, just to enter everything into the system, the supercomputers will take over, and based on an AI-driven design method, generative design, the optimal solution is created. And what you get in the end is not just a solution, it's the best solution for the problem that you have described. So if you compare the conventional design method with generative design method, is you not only come to better solutions, since now you get to the best solution, while otherwise you come to a solution, you also did it in way less engineering time. Of course, yeah, you have the time of your computer, which is calculating, but let's be honest, you can let your computer run, well, in this case, it's a supercomputer provided by us, but you can let it run overnight, you can let it run over the weekend, over your holidays, during Christmas and New Year. It's always working, it's a computer system, that's the advantage. While if you have those things with conventional way of designing, yeah, you end up in losing time, getting delay in your project, and so on. So we try to change this way of working to get to less meetings, less guessing of concepts, less manual iterations, because those cost a lot of time. And if you combine this with additive manufacturing, and I think that's one of the keynotes that I want to bring you during this webinar, if you combine this with additive manufacturing, you can use a full freedom of generative design, because you can get to very complex designs. And in the meantime, you can get the full freedom of additive manufacturing, because it's very hard as if you just want to design something, if you create something, it's very hard to create very, very complex 3D structures. It's hard to think in that way. And combining generative design with additive manufacturing is really pushing the boundaries of both technologies here. So let's have a look then how this would look for this case. So in general, the flow is we start with the design setup. Then the generative design part will take place. That's running the design on a supercomputer, and you immediately get to the final product, which you can download as a step format and send immediately towards your additive manufacturing capabilities to print it down. But let's have a look in our software how you would do such a setup. So once coming on the platform, you have an overview of all running projects. For today, we are working on the Wafer Table, so I will open up that platform, and what you see then is an overview of all the cases that you are running. We will immediately go through the case setup and the post-processing that you would need to do in a case like this, but you can see already that there are 2 finished cases. Those are cases that I submitted a while ago already to be able to show you the result as well. But let's start with doing a case setup. So we'll call it temperature gradient minimization. Webinar, just that I know that it's for this webinar. And then you need to select whether you just want to simulate a geometry or that you want to simulate or create a design with generative design. That's the case in this case. So you select design, you add the case, and then you are coming to the setup, which enables you to upload a step file. What is now in this step file is basically this solid geometry. a fluid geometry, and the design region. And you can really see that as the wafer table without any cooling structures in it. So basically an empty geometry and the corresponding fluid region. And in this fluid region, in the design region, or with the design region, we indicate which part of the fluid region may be used to create a design and which not. So basically you're giving the design envelope to the system. And that's what you get then, so you can visualize it as well in Diabatix Coldstream. as you might have seen in the slide deck already, we are optimizing today on just a part of the full wafer table. It's just to give an example of the system, so it's not on the full geometry. So let's go through the setup then. On the left hand side, you see the two regions. Let's expand them and let's hide one. So you can see this is a solid region, which is an empty at the inner side. And then first step that you need to do is indicate what type of region it is. Is it a solid region or is it a fluid region? In this case, it's a solid. And let's give it a name as well, Wafer Table. And then you can select a material as well, which is in this case aluminum, silicium, tin, magnesium. Voila, we do have a default library of materials, meaning you can easily select materials. If you have some specific materials, you can of course add them to the library and they will be available for you, but not for other companies, of course. What you can see then is that there is a boundary added to this geometry, and let's only visualize this one. This is the patch where we want to apply a heat load to, and then you need to select again which type of boundary it is. Is it a fixed temperature wall? Is it a heated wall? Is it an external wall? In this case it's a heated wall. I'll also just give it a name, and it has a heat generation of 10 watt. So this is basically your input. Let's go to the second region then. That must be the fluid region. So it's a fluid. And again, you need to select which type of fluid it is. Is it air? Is it water? Is it a certain mixture of water glycol? In this case, I will just take water with the properties fixed on 20 degrees Celsius. And you need to select the turbulence model. That's the next step. You have a few options available, and if you don't know which one to select, we always give a recommendation, and in this case it's K omega SST. So let's go for K omega SST, and then you see that there are a few more layers as subregions in this region. That's what you can see in the region tree. So let's start with the subregion. That's then the design region. So basically this is the part of the fluid region where structures may be added. It's like a little bit like if you would ask a colleague of you to design something for you, and you would say, in this region you may place structures to optimize the cooling. That's this, but you're explaining it to a computer system instead of to a colleague. So let's call it design. And then you can select again a material which is added, which is in this case just the same as the solid region. And you can select a manufacturing method with the corresponding manufacturing settings. Voila, then let's go to the two boundaries which are added, that are the inlet and the outlet patches. Let's start with the inlet, or with the inlet patch. That's the one at the outer side. Again, you have different options going from a pump inlet to pressure inlet or fixed flow rate inlets, which is the case in the last one. So you give the inlet temperature, you also give the mass flow, which I need to look for a second. So, and the mass flow is expressed in cubic meter per second, 0.000125. So that's it for the inlet. And we also need to define the outlet, of course. And that's just a pressure outlet, meaning that we fix the pressure at that place to 0 Pascal. So now we have created the boundaries already. We have given some information about the design space. We have given some information about the manufacturing setting. Next thing that we need to do is give a pressure loss constraint, since the pressure loss was limited in this case. And how do you do that? Since we have fixed the pressure at the outlet to 0 Pascal, we will put a constraint on how high the inlet can go. And that's 70 kilopascal in this case. And you just select the inlet patch again at target, select pressure loss, and you enter the value, which is the maximum. Last thing that we need to do before we can submit a case is say what we want to minimize or what we want to optimize. And that is in this case the temperature variance on the heated wall. So we select the heated wall again, you add a target, and you select temperature variance minimization. And that's it. Only thing that you need to do then is validate the geometry. Now the system will check if all the boundary or all the boundaries match all the geometries, which is in this case approved, and then you can submit the case. Last thing that you need to select then is whether you want to run this on a detailed level or a conceptual level. Detailed is on a very accurate mesh and to get a very detailed result, which is fully ready for manufacturing. Conceptual is on a rougher mesh. Results are a little bit less accurate, but it's just to give you a first estimation of your result. What is possible? It's more like to get what is feasible with your design and how far you can go. And then you can also select if you want to run this with 100 credits or 85 credits. That is basically representing how many cores you're putting through this job, and that depends of course as well on how long it will run. For this case I will select detailed design 100 credits and I click OK. The case is now sent to the supercomputer and I will get a notification in my email box when it's ready. So, but as I said, I have submitted this case already a while ago to be able to show you the results as well in the platform. Now we will have a detailed look as well in the presentation on the result to compare it with the other simulations. But let's have a look as well on how this look in the software. So if you enter a case, you are able to see a summary of the results, and you can change the dimensions as well to make it a little bit easier to have it all post-processed. And then you can have an overview of all the relevant temperatures, the pressure losses in different units again, an overview of your input, and a little bit information on, for instance, the imbalances. You can also download the result, which is of course also interesting, and you can visualize the 3D result. What you will be able to see then is basic post-processing module of your case. So you will be able to visualize the temperatures, you will be able to visualize things like the pressure and so on. So here we go. You can see the case now, and here on the left hand side you can see the structures again, which we added in the pre-processing. I will quickly hide some of these, and let's have a look first for the design which was created, which you can see here. So you can really see the 3D geometry here, and for instance let's give it a color according to the pressure. Voila. So and now you can really see the 3D structure which was created. Voila. We can visualize it as well with some streamlines, which we can also color, for instance, according to the velocity. And then you can see really good how well the fluid is spread in this design. If you compare it, for instance, to what we have seen in the pin-fin design. Voila. Let's have a look then as well for the temperature spread. So let's visualize the heated wall and rescale it to the same scale as we had for the previous results, and then you can see how good the spread looks. So it's a very basic post-process module, just to give you a quick overview of how the results look. And from here on, you can then also download the results. So let's switch back to our PowerPoint. And that's how it looks in the Diabatix Coldstream platform. So you really can see the engineering time, so the time that you need to spend to get to your designs is very limited. It takes a little bit of time to run the generative design, but in the meantime, you can work on other products, or you can work on system level, or do other stuff. The design is created for you. Let's have a look as well to a summary of the results and evaluate again the same 3 key parameters. Let's start with that. So the thermal gradient was at 0.10 degrees Celsius. It's a little bit higher than what you had with the serpentine design, but your system couldn't handle that because of the too high pressure drop, and still the thermal gradient is within the acceptable range. Pressure drop is at 40 kilopascal, so also within the range which is acceptable, and time to stable is at 381 seconds, which is significantly lower than what we have seen so far. So if you would compare it with the 2 other designs with the conventional method, this is the only design which fulfill all your design requirements, and that's really the challenge which we see and that are reoccurring in all the problems of our clients. Problems like this are becoming very, very complex. The demands for pressure drop, for temperature gradient in this case, or with you see the same with battery cold plates and so on. It's becoming so complex that it's very difficult to solve with conventional way of engineering. And if it is solvable by that way, it costs a lot of time. And if I have learned one thing over the past year, it's that time is one of the most valuable things in engineering. With a system like this, you can reduce that significantly. Let's have a look for some other pros and cons, of course, for this design. So the design is fully automated. That was what I was highlighting already. The fluid spread is fully controlled by the system, so it might be that a full fluid spread is not necessary, but the system will decide it. In this case, it was really necessary, and you can see as well that the fluid is very well spread. It's a specific solution for one problem, but power removal and chemical cleaning is a little bit more difficult if you compare it with a pin-fin design. It's not as difficult as what you saw with the serpentine design, and Scott guaranteed me that for a design like this, and a company certainly, well, of 3D system is certainly capable of cleaning a design up like this. The disadvantage of geometry like this is you can see it's very complex, and that makes it as well that CAD files are very hard to handle. So it's not that you can start again from this design and upload it in a parametric tool to do other stuff with that. So that makes it more difficult. But in my opinion, that's also not necessary. You design for a certain situation, you get to the best design for that, and in the end, you get the best design for that situation. So there is no need to change that anymore. So it is something that you need to take into account and that you need to be aware of. But due to the changing workflow, that is not really of a problem. And if we summarize then all 3 of the results, you see in terms of thermal gradient, the serpentine design and the generative design were performing well, while the cooling fin area was not good enough. If you evaluate the pressure loss, you see the opposite. Well, the generative design is still performing well. The cooling fin design also, but the serpentine design had a way too high pressure loss. So to conclude, generative design is solving all of the design constraints here, which was not possible with the conventional way of designing. So that's for the design part. Let's have a closer look as well to what that would mean in terms of manufacturing.
Yeah, thank you. Yeah, great summary. Let's talk a bit about how we end up actually making this. Here we're taking a look at a cross section of the part. So the top has been chopped off so we can appreciate what's inside. Now, typically this would be printed fully enclosed, so it would look like a fully enclosed disc, and it would be kind of mysterious what's inside, but you would know as you had designed it. So we printed this pie, what we call pie section, on a DMP 350 machine, and this fits nicely inside the 350, and this is just a sample demonstrator. We printed this in aluminum 6061 RAM2, which we offer through our AIG service, as well as to customers. We have parameters available for them. Now, on a full-scale wafer, 300 millimeter wafer, you'd want to put that on a larger system, larger volume system like the DMP 500. DMP 350 could handle smaller 200 millimeter wafer tables or cooling tables. But if you're at like a 300, 400 millimeter cooling table, you would want to go to our larger frame system we'll talk about in the next slide. And from a post-processing perspective, heat treat was applied to this. We have various heat treat options we have experience with across our material portfolio. And this was set up completely flat on the build plate. So a wired EDM process will create a precision flat bottom surface. And in this case, we used simple vibratory powder removal. And in the fully enclosed use case, where we're actually practically applying this, we would use chemical etching or chemical cleaning to clean out those interior channels. And we've shown practical results of almost zero particulates, in many cases zero particulates through the chemical cleaning process. And across our material portfolio, we have slightly different techniques to clean the interior channels to ensure that we adhere to high cleanliness requirements of the clean rooms for semiconductor foundries. And the final thing you'd want to do is do a leak tight check. And typically, when we go into a production process like this, we'll print some small section, like one of these pie pieces, with fittings, and do a leak check first to ensure that the design can be trusted and scaled to the entire platform. And you may have various non-destructive testing requirements, such as CT or ultrasound, just to verify based on your own company procedures and policies of the density of the part and the integrity of the part. And with that, what we'd like to do is talk about some of the more details about the elements of our solution. Now, 3D Systems is not only a component of the solution as a solution provider with Diabatix, but we're also a tool builder. So we are a manufacturer of direct metal printers as well as polymer printers. And here you can see what we call our mid-frame systems, DMP Flex 350 and the Factory 350, with a build volume of roughly 275 by 275 by 420. So a little bit higher in height than in XY. In this case, we're best in class low oxygen environment with the argon flooded environment that gives us high purity and low porosity of the process. We also offer real-time monitoring so that you can inspect and collect data and anticipate possible events, which would contribute to part quality issues without having to do destructive or non-destructive testing. Now, for larger volume parts, we would want to take a look at the DMP 500, Factory 500 solution, which is a full 500 millimeter cube. And it's a good choice for large volume parts, not necessarily for high quantity serial production. It's our specific choice for larger volume wafer tables or larger volume semicon components that don't fit on the 350. And we have these available in our AIG network. Let's talk a bit about materials. Now, I have this ordered from left to right in what we're commonly seeing in wafer table applications and semicon in general. Quite a bit of aluminum uptake in semicon, and we've just recently released alloy in partnership with AP Works and aluminum 6061. We're seeing still quite a bit of the traditional ALSI 10MG, though in some cases the silicon content is not appropriate for the application due to contamination considerations in the wafer system. But still, we do see many of our wafer table applications are based on aluminum. We do offer, of course, the typical and traditional titanium grades you would find, and those are very valuable for fluid flow applications, high strength to weight ratio, and areas where you'd have non-corrosive environments. And we offer 316L, which we commonly see in semi-cap for semicon capital equipment. We are seeing the traditional kind of 718 and 625 Inconels being used for their corrosion resistance and not for their temperature resistance. Those alloys are highly resistant to corrosive fluids and gases, maintain their structural integrity with good strength to weight ratio as well. We're seeing much less, almost no cobalt chrome or tool steel in semicon, but those are alloys that we do offer. And to cap all this off together, we do offer a complete build system from a software perspective. On the next slide, we can see more about 3D Expert. And very unique software which allows vector level control. So you have total control over your parameters and drawing styles, not only per layer, but also per 3D geometry when you build a part. And it's got all the traditional kind of healing and fixing things you might expect from meshes, but a key feature here is that we do slice BREP CAD directly, and we can slice hybrid models directly. So if you have a generatively designed result infill, you can put that right on top of a BREP file, and we don't care what source data it is. We can slice both together and create a single slice file. And that also comes with build simulation, which allows us to check the build risk and predict the build quality. That comes with 3D Expert. And you can do some level of post-processing downstream for NC machining.
Okay, and let's have a look then as well to which elements were there on the generative design side. First of all, as I demonstrated, of course, the Diabatix Coldstream platform came in, which the focus of is optimizing thermal and flow. What you typically see there is, in terms of performances, we can end up with 30% reducing or 30% improved thermal resistances, improved heat transfer, lower pressure drops, which you have clearly seen in the examples that we showed, and much more. And of course, as well, especially in complex situations as this is saving a lot of your time and of course reducing cost as well. And this process is exponentially making your design cycles faster. Besides that, if we have a look to the combination with generative design, one of the key elements of this platform is a greater freedom. You can go behind human imagination, and then if you have a look to the design, this is meaning a lot more complex geometries than what you would get with conventional engineering. So the design freedom is much bigger. And beside that, because typically if I say, hey, you will get much greater design freedom, people are always, yeah, okay, but then we cannot manufacture it anymore. It's one of the key elements of this system is that it immediately incorporates manufacturability. That's why you saw me selecting the manufacturing settings while doing the case setup. It's because those manufacturing settings are taken into account during the design process, meaning that the design that you get in the end is manufacturable by the parameters that you selected. And that's all done by the Diabatix Coldstream platform. The platform itself is very easy to use. It's just an in-browser software. So if you have like Google Chrome or Firefox on your computer, you don't need to install anything anymore. You also don't need to have a very powerful combination to run this. As I have said a few times, it is computationally very extensive, and you need a lot of CPUs to run this. This is backed up by Diabatix. So we provide you with the necessary cloud computational power in order to get your complex designs in a fast way to the most optimal result. And this technology, so the combination of supercomputing and generative design, is used in automotive designs, like you can see here, or electronics designs, or semiconductor industries, with always the focus on faster time to market, reduce your engineering time, and of course, a very high thermal performance. So those were the key elements on the case study that we did, and to give an example of what the combination of additive manufacturing and generative design could mean to you. We'll take the opportunity to show you a little bit as well on how the cycle would look, and we would like to direct you as well to some places where you can find more information. Scott, can you maybe enlighten us a little bit more about this approach?
Sure. Now, again, this is just a reminder of our approach together. What we intend to do is de-risk the process of combining generative design and additive manufacturing. So because of that, what we'd like to do together is both Diabatix and 3D Systems come to evaluate or explore some potential areas of contribution to your engineering and your system, and participate together in an innovation process where we can help guide you to a possible solution through the combination of these tools. And then we would go through the process of, figuring out how to make it, how much it's going to cost, how long it's going to take, and do all that work together. So you're learning along the way, and we're de-risking the process so that if you do take on the technology, or you take it on between yourself and a supplier, you can be productive almost immediately, and the training time is quite minimal. And on the next slide, I do want to draw your attention to the Metal AM issue, summer 2021 issue. Gert-Jan and I worked closely together along with some of our teammates and colleagues to develop a deep dive discussion on semiconductor capital equipment, as well as specifically cooling patterns. And this presentation today was to expand on that and develop it more. So please do take a look at that and read it. And I would encourage you, if you are looking for more information, to visit our 3D Systems website, as well as the Diabatix website, and submit a request for contact, and we will come to you and try to work together to start solving your problems.
Okay, thank you, Scott. So that brings us to the very end of this webinar. We are running a little bit out of time, but seeing the topic, I hope that's not a problem for any one of our listeners. First of all, Scott, I would like to thank you for attending this webinar and enlightening us so much about additive manufacturing, and of course as well for the cooperations that we had in this project. I think we brought out a very interesting case study, and that we are really showing the world nowadays what the combination of generative design and additive manufacturing can mean. And those are, in my opinion, two of the most innovative technologies which are out there, and I think they in the future they can even more change the way we approach engineering.
Yeah, thank you very much. Thanks for the opportunity to work together.
Okay, well, it was a pleasure. Last but not least, I would also like to thank all our listeners. Thank you for attending today. The webinar will be available for recording afterwards. You will receive an additional email for that, to access that. So also, if you had any of your colleagues who might not be able to join today, or that they are just interested, you can always forward those links, and they can request access to the recordings as well. And by that, they can as well view it. So thank you very much all for attending, and I hope to see you again in our following webinars. And in the meantime, if you would like to have any more information on this topic, contact us directly via the 3D Systems website and the Diabatix websites, or contact Scott or me directly. Have a look for the Metal AM article, and then we hope we can enlighten you even a little bit more than today. Thank you very much, and see you later.
Thank you. Bye-bye.